Hello, I'm Gabriela, a PhD student at Johannes Kepler University Leeds, and I will present to you a new solution to the ArgoUML SPL challenge case, spectrum-based feature localization, a case study using ArgoUML. This is a joint work with Bruno, Jabier, Aitor, Abreu, and Wesley. The increasing demand for tailored software-intensive products makes companies start considering the transition from monolithic single-purpose systems or families of systems created with an opportunistic copy-paste-modify approach to higher levels of systematic reuse for the creation of variants, such as the software product line. And software product line consists of a core and a set of features that can be reused to tailor different products of a system, where a feature can be any system functionality. In this context, feature localization is a basic activity in re-engineering legacy systems into software product lines, known as extractive software product line adoption. Feature localization consists of taking some feature information as input and recovering the traces from where this feature is implemented, for example, source code classes, methods, etc., depending on the desired results granularity. Some techniques are proposed to semi-automate or automate the feature extraction process. Feature localization techniques can be, for example, dynamic when are based on the system execution to obtain traces, or can be static depending on the textual information of a set of existing system variants, as well as control or data flow dependencies, or hybrid combining two or more feature localization techniques. Benchmark was proposed for comparable results in feature location for families of systems. The use of benchmarks in the software product line research field has been acknowledged as an important direction to advance the state of the art, and for this specific benchmark, static feature localization techniques or feature location techniques have been proposed to locate features in sets of variants, as well as a hybrid approach. In our work, we focus on dynamic feature location and we explore the usage of spectrum-based localization. Similar to the hybrid approach from Michelon et al. 2021, we consider only the regional scenario, that is the single system of the regional ArgoUML with all features, aim to contribute to the state of the art of the feature localization or feature location for re-engineering single systems into software product lines. Therefore, our goal is to present a dynamic feature localization technique for re-engineering single systems into software product lines. This work contributes with a dynamic feature localization approach using spectrum-based feature localization based on previous work from Castro et al. 2019, and a comparison of our approach with the previous ones, the static from Michelon et al. 2019, and then a hybrid approach from Michelon et al. 2021, evaluated also with the ArgoUML SPL benchmark. We also made available the source code, instructions, and results data for reproducing or reusing our solution, or reasoning with the results. Spectrum-based localization techniques have been mainly used for fault localization by exploiting coverage information of test cases to calculate the likelihood of each software component being fault. The spectrum fault localization follows the assumption that components which are frequently involved in failing tests are more likely to contain the fault than ones that are frequently involved in passing tests. In this figure, we can see a spectrum where each trace shown in the columns represents a test case, and the nodes shown in the rows are the lines of code of the program, understood with a 1 when the line has been executed at least once for this given test. And the last row is the result of the test with 1 when the test passes and with value 0 when the test fails. Using a spectrum, numerous ranking metrics have been proposed to create a ranking of suspiciousness, that is trying to point developers to the lines that are potentially creating the issue, or at least narrowing the part of the source code that's worth to examine or debug. Here we show two well-established ranking metrics, OSHI and Tarantula, where the NCF is the number of failed test cases that cover a node, and F is the total of failed test case, and NCS is the number of successful test cases that cover a node, and NS is total number of successful test cases. Each node, for example, can be a line of code, is assigned by the ranking metric with a continuous value normalized to range from 0, which means apparently completely unrelated, and to 1 when it is apparently faulty. Values in between will have to be analyzed under a certain user-defined threshold. In this work, we use this approach for feature localization using a spectrum like in the picture on the right side of this slide. Compared to fault localization, our traces are executions of the program purposely exercising a given feature. For example, from manual executions or test executions that we know are related to a given feature. And the result will be 0 for the traces that belong to the feature that we want to locate, that is, as if it was the faulty code to locate, and the obtained ranking when apply one of the ranking metrics will be based on the suspiciousness of each line of code belonging to a feature under analysis. We now show our study design and execution. We first need the exercise of the features, which we reused from Michelon et al. 2021. These traces were made publicly available in files with data about the lines of code that were executed per feature. Two scenarios were analyzed. So we have manual exercises of the features and also exercises from existing tests that are related to the features. The supplementary material of Michelon et al. 2021 contains the tests that are 1,198 in total, and the videos of the manual feature executions, as well as the traces in text files. As a characterization of this feature exercises, we calculate the total number of lines of code executed for each feature, and as the results, the average of manual executions were around 36% of the lines of features executed, while the average of test executions is around 4% of features lines of code executed. Despite of low coverage, creating our own manual executions or using different tests might introduce a significant bias as given the nature of dynamic approaches. The obtained results are highly sensitive to this input, and by reusing the feature execution files, we could be able to compare also our results with the results reported by the hybrid approach from Michelon et al. 2021. With the execution traces, we performed the feature localization. We used a spectrum-based localization, as mentioned before, and with two key aspects for this spectrum-based localization techniques: the metric used to rank and the threshold to decide when a line of code is suspicious enough to be considered part of a feature. The threshold is needed as the benchmark does not consider probability as part of the metric's computation. We implement the spectrum-based localization technique using an existing Java library, and in this work, the results are reported by using several combinations of 33 ranking metrics and 10 threshold values for each ranking metric, varying from 0.1 until 1.0. The goal here is not to overfit the technique to this dataset by using those 330 combinations, but to provide an overview of what can be the results of a spectrum-based localization. Regarding how we perform the comparison with previous work from Michelon et al. 2021, as in this work, metrics are based on line and method level due to existing feature location techniques being limited to method level or do not yield satisfactory results when applied to single systems. We then reuse the code to calculate the line and method level from Michelon et al. 2021 and be able to compare the two feature location techniques in equal conditions. In addition, Michelon et al. 2021 computed the benchmark metrics, similar to statement level. However, the execution traces granularity is at the line level, and then the results are also based on lines of code. So it's not straightforward how to transform them to the convention established by the benchmark. This convention mixes class level, method level, and refinements of classes. We implemented our own transformer with a simple implementation consists of always adding a class level localization when there is at least one line in the class. By using this naive approach, which does not consider methods or refinement tags at the class and method level, we assume a certain loss in recall. Now regarding the results, comparing with the hybrid approach, the static analysis implemented in the ECHO tool, which is used by the hybrid approach, mining overlapping traces from the execution traces. And in the hybrid approach, the feature localization is intended for re-engineering single systems into software product lines, for creating variants which should contain the base plus a set of feature-specific source code. Thus, line and method level metrics reported in Michelon et al. 2021 consider true positives not only the feature-specific line and methods, but also the source code that is in common for all features that they call as base of ArgoUML, the core of the system. For the spectrum-based localization techniques, including the source code of the base and the precision recall metrics, is not potentially beneficial, given that the standard ranking metrics are not designed for identifying the base plus the target feature, but only the target feature. However, we can see that the results are also competitive in this comparison. In this figure, we show the precision and recall of the different ranking metrics for the manual execution using the line level metrics defined in the hybrid approach. The vertical dashed lines show the boundaries regarding recall, given that even if we include all the source code executed through the input execution traces, these execution traces did not include all the feature source code at all in the base code. So in this figure, the average of the 6 diagram features from manual execution from Michelon et al. 2021 approach mostly dominates at line level. The dominated area has a light background, as you can see. However, ranking metrics, it's the extremes of precision, for example, VONC to 1.0, and recall, for example, Hamming 0.1, are also part of the Pareto front that is non-dominated solutions. At the method level, compared with the hybrid approach using the manual executions, the spectrum-based localization technique get closer to Michelon et al. 2021, even if they were not specifically designed to locate the base source code. In this figure, we show the comparison with the hybrid approach using tests execution with 8 features of the ArgoUML. In Michelon et al. 2021, the line level dominates in terms of precision, but several spectrum-based localization techniques are close to it, such as VONC 1.0, which also has a higher recall, and the highest precision for spectrum-based localization is obtained with VONC 3 and threshold 1.0. At the method level, with tests execution, we have solutions that slightly outperform both in precision and recall, such as VONC 1 with 1.0 threshold and OSHI with 0.1 to 0.3 threshold, are tarantula from 0.1 to 0.5 threshold. In this figure, we show the comparison between our own transformer to benchmark convention for the manual and test exercise of the features with the hybrid approach presented by Michelon et al. 2021 using the benchmark convention, and also compare with the Michelon static approach from 2019. The latter is successful in scenarios with an increasing number of variants, and it also considers feature interactions. From this static approach, we include only the results in the benchmark scenario with only one variant and using the average of the considered features. The highest precision is with manual exercises obtained with the same values for different ranking metrics. So it is, for example, VONG2 threshold 0.9 to 1, or OSHI from 0.8 to 1, or, for example, tarantula from 0.9 to 1, among others. Those are also the ones that obtain the highest F1 harmonic mean of the precision and recall. For recall, not surprisingly, the highest values are obtained with low thresholds with different techniques. For example, Wong 2 0.1 or Hamming 0.1 and others. We can observe how Michelon et al. Static approach from 2019 is in the Pareto front because of its recall value. The Michelon et al. Hybrid approach from 2021 got lower values in both precision and recall compared to our technique, spectrum-based technique. And we're using the thresholds, for example, impulse 0.5 to 0.6. In this figure, we show the results for the testing exercise for all 8 features, including the diagrams, logging, and cognitive features. In this case, the results from Michelon et al. 2021 dominate the spectrum-based localization technique in both dimensions. The ones closer to Michelon et al. 2021 are VONG2, tarantula, Hamming, arithmetic mean 0.9 to 1, Underberg 0.4 to 1, OSHI 0.8 to 1, and OSHI 2 0.7 to 1. Regarding the performance, the dataset reader takes around 18 seconds as it needs to parse all the execution traces files. After that, for the creation of the spectrum, the computation of the ranks using the ranking metrics for the 6 features diagram, getting the results under the defined threshold, which we force it to be 0.1 for all the runs in the performed experiment as the worst case, given that most of the nodes will be retrieved this way, took less than a second or around a second. As already acknowledged by the fault localization community, there is no optimal ranking metric in practice. We provide the results of the ones that obtain the highest precision recall with their corresponding thresholds as candidate suggestions. For example, VONG2 1.0 seems appropriate if precision is to be optimized. The results also depend on how one exercises the features, as we could see by the coverage of the features from execution traces from Michelon et al. 2021, which are relatively low. This shows how much recall is affected by the execution traces and how much dynamic feature localization could be improved to reach higher recall. Standard spectrum-based ranking metrics obtain competitive results using existing execution traces compared to a previous hybrid approach from Michelon et al. 2021. As further work, we consider calculating feature interaction locations and use other benchmark scenarios with several variants to refine the results through hybrid approaches. Also, techniques combining ranking metrics through a machine learning phase with already located features can be explored. Thank you for your attention, and any further comments or doubts, do not hesitate to contact us.